The question I have is, could you do an example on adding 3D forces by the algebraic method? This is the third example I'm doing on the topic, and in this example, we will focus on the application of the position vector method. This is the problem that I have selected here. We have a vertical tower that is being supported by two cables. The tension on the cable AB is 2 kilonewton and the tension on the cable AC is 3 kilonewton. The force acting at point A by this cable is directed in that direction, and the force acting at point A by this cable AC is directed in this direction. With respect to this Cartesian coordinate system XYZ, the coordinates of these points A, B, and C are given. So we need to find the directions of these cables, which in turn are the directions of the forces by the position vector method. The question is to find the resultant of the two forces acting at point A. Remember the details of the position vector method, right? To write a force in its component form, we take the magnitude of the force and multiply that by the unit vector in the direction of the force. In order to find the unit vector, we use the coordinates of 2 points on the line of action of the force. So if I take FAB, the force on cable AB, this is the line of action, and our choice is to use these 2 points, point A and point B, both of which lie on the line of action of the force, right? So let's go ahead and find the vector from A to B. If I call that as RAB, RAB is given by this equation. The x component of that vector is xb minus xa. The y component of that vector is yb minus ya. And the z component of that vector is zb minus za. So to avoid confusion, I recommend that you first list the coordinates of the points involved in the problem. So here we have 3 points A, B, and later on we need point C as well, right? So what are the coordinates of point A? Well, point A happens to lie right on the y-axis, right? And therefore the x-coordinate is 0 and the z-coordinate is 0, right? And the y-coordinate, you can see easily, measuring from the origin, is just 5 meters. What about point B? Well, point B happens to lie on this plane, xz plane, and therefore the z-coordinate, the y-coordinate of that must be equal to 0, right? So we have a 0 here in the middle. The x-coordinate is the distance from the z-axis in the x direction. So you can see that's that distance right there, but B happens to lie on the negative side of the x-axis, and therefore the x-coordinate is minus 3. And the z-coordinate is 2 with a positive sign because point B happens to lie in the positive z direction. Similarly, point C happens to lie on the xz plane, and therefore the y-coordinate is 0. The x-coordinate is simply 6 meters, and the z-coordinate is 4 meters. So that's what I have here. So it's good to define the coordinates of these points once and for all before you start doing these calculations. Now it's fairly easy to substitute numbers for them because we already have them right here, right? xb is minus 3, so I have minus 3 here. xa is 0, so I have 0 here. yb is 0, and ya is 5, and zb is 2, and za is 0. So those are the numbers you see here. Simplifying, we get this for the vector RAB. So once we have a vector in terms of its components, how do we find a unit vector along that direction? Well, we find the magnitude of the vector and then divide the vector by the magnitude. That means you divide each component by the magnitude. So let's go ahead and find the magnitude. Here is the magnitude of RAB. That will be square root of 3 squared plus 5 squared plus 2 squared, right? So we get a value of 6.164 for that. Here is the unit vector from A to B. We get this in its component form. The final step of representing vector FAB in its component form is to multiply its magnitude by the unit vector. Magnitude is 2 kilonewton. and this is the unit vector. So here we multiply the two, and after simplifying we get this. So this is the component form of FAB. Now we repeat this in order to find the component form of vector FAC. Here are the details. Fundamentally, the steps are identical to what we did for FAB. So I'll let you follow. So we have this as the component form of FAC. Here's a summary of what we got so far. Here's your FAB vector, here's your FAC vector. We add the two in order to find the resultant. So this is what we have for the resultant. Here is the calculation for finding the magnitude of F. So we get a value of 4.041 kilonewton. And here are the details of finding the direction angles of the resultant vector F. We get these values for the direction angles of the resultant vector F. You may note that this angle is greater than 90 degrees. That is because we have a negative sign in here, so that renders this angle greater than 90 degrees.